Okay, sure. So I guess the time is up. So perhaps we start now. So good afternoon, good morning, good evening, everyone. Happy Chinese New Year of Ox, and so welcome to the TMS Talk, Season 2, Episode 4. I'm today's moderator. My name is Pai Zheng, and I'm currently a assistant professor from the Hong Kong Polytechnic University. And my research area mainly focuses on the smart product service system, engineering design of informatics, and digital servitization. So for today's talk, I will first have a brief introduction of our society, as well as many new friends joining us today. And then I will briefly introduce today's speaker, Dr. Yunlong Tang, who will share with us his exciting research progress. And it will last about 40 to 50 minutes. And after the talk, we will have a 30-minute Q&A session. And perhaps since I'm perhaps the only host, and I will lead the Q&A session as well. So firstly, about the TMS and or the Lattice Society, for short, is a non-profit organization that aims to build a community for young scholars to freely and equally build connections, share their work, and exchange thoughts. In season 2, we are having our traditional events, TMS talk for academia, WBA talk for non-academia, and TMS workshop for skill sets building. In addition, we introduced a special issue at the beginning, the very beginning. The topic of the special issue is based on what our audiences and members suggest. So if you have any suggestion for our next season special issue, please let us know. And also for more information, you can always feel free to visit our website and subscribe our WeChat and Twitter channels by scanning the QR code. So for any questions, please email us. And now today, it's our great honor and pleasure to welcome our guest speaker, Dr. Yunlong Tang. Dr. Yunlong Tang joined the Faculty of Engineering at Monash University in 2020. Currently, he's a lecturer joint appointed by the Department of Mechanical and Aerospace Engineering and the Department of Materials Science and Engineering. His major research interests are in the general fields of design and manufacturing, including smart manufacturing, additive manufacturing, and its related design methodologies. Sustainable design and manufacturing, AI-aided design, CAD/CAM, design and fabrication of lattice and cellular materials. Yunlong has over 9 years of international research and development experience, participating in several national research and industrial projects from China, Canada, Europe, and Singapore. He obtained his PhD degree from McGill University, Canada in 2017. Master of Science degree from Beijing University of Aeronautics and Astronautics. Now it's Beihang University, China in 2013, and Bachelor of Science degree from Harbin Institute of Technology in 2010. Before he coming to Monash, he did 1.5 year postdoc research at Singapore University of Technology and Design, and was working on the next generation of CAD software for additive manufacturing. He's a leading developer of an open source lattice structure design and optimization software called Lattice Pro, which has been downloaded for more than 10,000 times to date. So I guess let's welcome, I will give the space to Dr. Yunlong Tang and welcome his talk.
My name is Yunlong, and currently, as the Pai has introduced, I'm working at the Monash University, Faculty of Engineering. I work for 2 departments, Mechanical Aerospace Engineering and Material Science Engineering. Because my research is, like, originally I'm from the mechanical, but yeah, like recently my research will, like, yeah, from my today's presentation, we'll see it's like hybrid. It's combination of the material and the mechanical. So the border between the material and the mechanical will be valued in the future, I think. So my today's talk is about additive design and manufacturing of our digital future. So this is the outline of my today's talk. It perhaps can take 40 minutes. And so we have the 5 sections. The first one, I will give you a quick introduction about the additive manufacturing and the beauty of additive manufacturing, especially for those people who are not really familiar with this type of the manufacturing process. Then I will introduce another very important concept I'm working on. Is called the digital hybrid materials. And we will give you the definition about what is the digital hybrid materials and some different type of the digital hybrid materials. Then, yes, our talk will focus on how to design the digital hybrid material. It's about my research in my research group. It's about computational driven design for the digital hybrid materials. At the end, I will show you some design cases and summarize with the digital future of the additive manufacturing, especially for the hybrid materials. So let's look at the first section. It's an introduction session. So in this section, yeah. In this session, the first slide, I want to give you a quick introduction about what is additive manufacturing. And when we talk about additive manufacturing, some people will think, okay, it's about 3D printing. But frankly speaking, additive manufacturing is not a single manufacturing process. It's a group of the manufacturing process if they can satisfy this requirement. It's a process of joining materials to make objects from 3D model data, usually layer upon layer. But you should notice not all the additive manufacturing process fabricate the part layer upon layer. Generally, we have 7 types of the additive manufacturing process. I don't want to read all of those names, but you should be noticed that the different type of the additive manufacturing process can fabricate or process different type of the materials. So in general, AM can work with a wide range of the materials from polymers, metal, ceramics, hybrid composite, which we are focused today. And also we can print the living cells. So the bioprinting is another hot topic recently. And why actually additive manufacturing bring us a lot of freedoms? Here I want to emphasize 2 words in the definitions. The one is joining. Because of the joining, the process, we build the part from bottom to up. So we can join material on different scales. On this slide, let me have the laser. So if you can see here, on this slide at the bottom of my slide, we see that all the parts are fabricated by additive manufacturing, but on different scales. On nanoscale, yeah, this is I think fabricated by the nanoscribe, but the figure is from the Caltech. And we can fabricate the lattice structure, theoretical lattice structures. The strike diameter will in the nanometers size. And each cell is about 5 microns the cell size. And on the micrometer, we can fabricate some features to have certain surface properties. On the mesoscale or millimeter scale, we can have the porous lattice structures to reduce the weight. Also, we can fabricate parts in the meter scale, which is the aircraft structure frame. And we can, by joining material, we can have the different structure on different scales. And also we can combine the different type of materials in one part. This is a demo that when I was still studying in Material University, I helped my supervisor to supervise the undergraduate student for their final year project to design a biomedical training model to train the medical student to the surgery for our nose. And because on the nose there are different type of tissues, the tissues with the different type of elastomodulus. So we use the different material in the single part to simulate the physical feeling of the medical training models. So we can join different materials. Even for the same materials, if we use the different process parameters, we will get different green structures. This is an example. And so in this research, the researchers use a different laser power so they can control the green size. So when we control the green size, we can have the different mechanical properties of the materials fabricated. So Generally, by joining materials, additive manufacturing provides us a lot of design freedom for the material process parameters. Another beauty of additive manufacturing is that it can be directly fabricated part from the digital model or 3D model. So it supports digital design and manufacturing. We can use our CAD software to design the complex structures. For example, here is the complex structures. On the micro scale, it's organic shape. And on the meso scale, we have some lattice structures. And yeah, you can never imagine that if you can use the conventional 2D hand draft to draw these figures and use the conventional CNC machining or other injection molding to make this complex structure. There's no way to do that. And another thing is only digital model is needed. That's the reason why additive manufacturing can have the quick response to any need. During the COVID pandemic, and yes, in the world, a lot of countries a lack of this type of PPEs, personal protective devices or equipment. And because conventionally we make these PPEs based on the injection molding, which is mass production. But to do that, we need first have the mold and dies, and then we can do the manufacturing. It will take 1 or 2 months for preparation. But during the pandemic, we don't have enough time to do that. So yeah, you will see a lot of researchers or the hobby makers, they use 3D printing to make the PPEs, and it saves a lot of people's lives. And another thing is that because it's directly from the digital design and manufacturing, so the whole process from the design, process planning to manufacturing can be fully automated. And there are some future factories, we don't need human to be there. The robot arm and can do it automatically. Design, fabrication, design can be done by the AI software, and the fabrication can be, and the preparation can be done by the robot arm. So the automated 3D printing factory can be implemented in the futures. This is about another beauty of the AM. So in the next session, my talk will mainly focus on the digital hybrid materials. Because of this beauty of additive manufacturing, we want to take use of those design freedom. One possible way is to design a digital hybrid materials. So you may have the questions, what is a digital hybrid material? First, we will go to the concept of the digital material. We will go to the concept of the hybrid materials. I think some of you may be familiar with the hybrid materials because it's a very classical definitions proposed by the Mac Ashby, and its definition is the hybrid material is combine the property of 2 monolithic materials or 1 material and space. So technically, we have 5 different type of the 5 different type of the engineering materials: the steel, the metal, the polymers, elastomers, glasses, and ceramics. But we can combine any of them, and then we will have the new type of the material called hybrid materials. So hybrid materials there are several types of the hybrid materials. Generally, why we need hybrid materials? Because, for example, we have the material which have the property in M2, property P1 in M2, and the property P2 in M1. And for the hybrid material, we want to achieve the material properties in the middle of them. So we combine the materials by different microstructures, and then we will achieve different points. But unfortunately, now we cannot achieve all the points in this bounding box. We can mostly achieve the bounding because there are some limitations. We can only achieve the D, C, B, but ideally we want to achieve A, which the material have the both material properties from the M1 and M2. So this is the hybrid materials. Almost like a natural material are hybrid. And then the next slide is about the digital hybrid materials. So I add the adjective here, the digital. Why we call it digital? Because digital hybrid material, of course, is a type of hybrid materials, but whose micro or mesoscale structure can be digitally designed and fabricated. So additive manufacturing is a digital manufacturing process, and it can help us to digitally control the meso or microstructure of the materials. And we use the computer aided design tool. We can control the microstructure or mesostructure of the digital materials. So here on this slide, I show you two different types of the porous materials, which can consider as a hybrid materials. But you see that one is the metal form, another is the additive manufacturing fabricated lattice structures or materials. The only difference between them is that in this group, we can consider it as a digital material since its micro or mesoscale structures are digitally designed and fabricated. We can control them, even though this one is randomized, it's like the form structures, but we can control the porosity distribution, the size of the size of pores, and also we can control the strat thickness. So that's the reason why we call this is a digital material. So in next several slide, I will try to give you some classification about existing digital materials. So first big type is called lattice or porous material. So you can consider about the lattice or porous material as a combination of the air to the solid metals or polymers or whatever. So according to the order of the material, we can divide them into two groups. The ordered lattice material, which the unit cells are periodically distributed in three-dimensional design space. And also we have the stochastic porous materials, which is like this type of form. The cells are not periodically distributed. It's randomly the size of the cells, the shape, and the strat diameters, they are randomly distributed. But we can also control the randomization. And the cell size can follow the certain like density, probability density distribution. So this is a stochastic porous material. For the other lattice material, we can also divide them into two types. One is a strat-based. So strat-based, to describe this type of microstructure of this type of material, we can use the cell topology plus strat thickness, the thickness of each strat. And also we have the surface-based TPMS. It's a joyous lattice structures. For this type of surface-based porous materials, in order to use the topology and the strat thickness, we can use implicit function, which is a surface function about these materials, and we can define the implicit function to describe this type of the materials. This is about surface-based porous lattice materials. Another big type of the digital hybrid material is called the voxelated digital hybrid material. 3D printing, you see that compared to conventional 2D printing, we have another directions. So for the images, we have the concept called pixel. And if we extend this concept into the 3D, so we will have another concept called voxel. Voxel actually can be considered as a very small, like a cube. So we use a polyjet or other type of additive manufacturing process. We can control the material distribution voxel by voxel. So this is the idea about voxel printing. So we can have a blue and red, the different color represent different materials. So we can control, actually now each voxel we can, with the advanced additive manufacturing, each voxel, the resolution will be achieved to about 20 micron. Each voxel, the length, width, and height will be 20 micron. It's pretty small. So we can control the material on the pretty small scale. And by carefully design the material distribution, we can achieve some like extremely mechanical properties. For example, this is the topological interlock structures. We can use this type of the topological interlock structure to stop the crack propagations, to increase the fracture toughness of the materials. This is the idea of the voxelated digital material. And in our research group, in my research, we also use this type of the digital voxelated material for some 4D printing like applications. And another type of the digital hybrid material is a composite, is a fiber reinforced composite. It's very, I would like to say it's very conventional, but why we call it digital and why we use additive manufacturing to fabricate it? Because for the fiber reinforced composite has been already widely used for like aerospace and other industries. But what unique properties or freedom that additive manufacturing bring to us? The first thing is that compared to conventional fiber reinforced composite fabrication process, so additive manufacturing can help us to fabricate the part with really complex shape on micro scale. Second one is that we can control the volume fraction of the fibers, and also we can control the fiber orientation. Conventionally, if you are familiar with the fiber reinforced composite fabrication, each layer we can have only uniform fiber orientation, 0, 90, 45. Yeah, so we can only have a certain degrees, and all fiber oriented in the certain angles. And everywhere we have the same fiber volume fraction. But for additive manufacturing, because we have more freedoms, we can digitally control the fabrication process using the toolpath. We can achieve the different fiber orientations in the structures, which can further improve the mechanical performance of the design part. Yeah, I will show you another example later in my slide how to achieve this type of the design. The last type of the digital hybrid material, I call it theoretical digital hybrid material. In the past few slides, I show you different type of the digital hybrid materials, but we can combine them on the different scales. This research has been done by the Greece, and he did really great job and try to simulate the do the biomimetic design of the naked and have this type of theoretical structure to increase the impact resistance for the digital composites and or digital hybrid materials. We can combine the complexity on different scales. So it means that digital material can be designed in another digital material. So we can have theoretical structures. This gives us more freedoms to improve or to explore the property of the designed digital materials. So as this is a quick introduction about what is the digital hybrid materials and why we need digital hybrid materials. The next part is about my research. From my PhD to my current research is trying to use the computational driven method to us to design for digital hybrid materials fabricated by additive manufacturing process. So first of all, I will give you introduce you another I think a really important concept. What is computational design? So there's no uniform definition about computational design hybrid materials. There's no expert to give the really strict definition about what is computational design. And this definition is given by myself and from my understanding. In order to help you to have a better understanding what is computational design, I want to do the comparison between the conventional design method and computational design method. So conventional, I think most of you have the have the experience to use the CAD software to do the design of the part. And so we have the human, it's you, the operator, who are in front of the computer like us today. And we use the computer and we have some software, the CAD software in the computer. And we use our hand to track the features, to define the size and then. So we actually, even though we work for 24 hours a day, 7 days a week, we only can, that it takes a long time for do the design. And we only have limited design options. We cannot explore all the design space. But for the computational design, instead of we use our hand to track the features and build the features. We use a design algorithm. We use the parameters to drive the design algorithms. So we define the parameters a range. For example, for the lattice materials, we define the lattice material will porosity or resistance will range from 0.1 to 0.5, and topology, I will define topology. We define the parameters. And we input the parameters inside the design algorithm. Design algorithm can generate thousands of options automatically by themselves. You don't need to use a hand to do that. And then use the advanced simulation tools, we can evaluate the performance of those designs. And then we can select the best optimal, not the global optimal, I would like to see, but the optimal design. So there are 5 pillars for the computational design. One is the parameter setting. Yeah, in the rest part of my talk, I will show you something about how can we parametrically design the hybrid materials. Another is a generative design algorithm. Is algorithm here to support generate different type of the design. And then we have the computer source. And this is then we get the data, get the result. We want to find the optimal result. We use some like surrogate model and we get the data and we use some optimizer to help us to get the optimal result. The last one is the 3D modeling and visualization. Yeah, some of my research also like involved in the 3D modeling and the visualization of this type of hybrid materials because yeah, commercial CAD software it cannot support you to design this type of the hybrid materials. It's time consuming if you try to modeling it on the micro or meso scale. So in general, the design of the digital hybrid material, if we use the computational driven approach, it involves the macro scale design because we not only design the macro scale of the product, the shape of the product or part. We also need to consider about what's the macro structure, what's the meso scale structures of the materials. So we have the different scales like the parameters on different design scales. On macro scale, we have the shape, and also we have the distribution of the material properties. Yeah, so because now we can control the micro or meso scale, we can have the heterogeneous materials. So in different places, we can have the different properties that can give us the better like functional performance. And on meso or micro scale, we can control the structures, the micro or meso scale structures. And also for additive manufacturing, another beauty is that we can control the process parameters. In the past, for CNC machining or other parts, for the whole part, we use the same process parameters to fabricate it. But for additive manufacturing, we can use the one group of the parameters to fabricate, for example, the thin wall, another group of the parameters to fabricate vertical, like a strap. So it can give you a different, so this relation is quite important. So process parameter, it will give you different structures. Different structure will map into different properties. Different property will give you performance. We have the design variables or design freedom on all those process structure and properties. And then we have the much freedom on the performance like level. So we can further improve the performance of our part. From this slide, I will show you some like research results from my PhD research until to current research. So the first one is the design optimization of the solid lattice hybrid structures. So in the past, we have the single like structure with the same materials, but now we can use additive manufacturing to fabricate the solid hybrid materials. But the problem is that where we should fill the lattice, and we developed some like heuristic optimization approach to help designers based on the stress mapping decide where to fill the lattice structures. Even for the design space for the lattice, according to the principal stress directions, we use the machine learning algorithm to help us identify the right cell topologies. For example, on the top and the bottom, because the principal stress direction is along this beam, and so we use this type of the cubic lattice cell. And at the middle, there are shear stress. So we use this a body cubic center lattice structure. So we use a different type of the cell topology field in a different region to further enhance the mechanical property of the designed structures. Another thing that I mentioned before is that we also do some research on how to design the heterogeneous lattice structures with the functional gradient property distributions. So for example, we have the property distribution like this, and we can map to the meso scale or micro scale structures. We can have the function gradient materials. We use a topology optimization and with some defined function mapping from the topology optimization result to the lattice result. So it can help us to further improve the structure performance. This is about structure performance. How about other performance? So another research I have done during my PhD is think about how to use a lattice structure for the multifunctional design for a part which can perform two more functions. This part actually is from the industry application, but I simplified because the IP issues. And for this part in the industry, they have the heat source on the top surface. The pressure at the bottom actually is a container trying to store some gas and hot stuff. And because they want to keep the temperature inside this gas, and so they have the heat source here. and they have the cold wall on the another two sides. In the past, if you all made if the structure of the made of the pure metal, and if you put the heat source here, the heat source, part of the heat will contact to the gas, but other heat will contact to the sidewall because the sidewall temperature is really like low. In this design, we want to use the lattice structures which can play the like performance as the heat insulation. So we want to use the lattice structure because for the lattice structure is a combination of the air and metal. If we see that metal has a high elastic modulus and high heat conduction coefficient, but air has almost a zero elastic modulus, and then conduction coefficient is low. We want to use like structures, lattice structures, to combine the two properties on different places. For example, here this is optimal design. We use a computational design approach to the optimization. We have this optimal design. In this optimal design, you see that we have the almost a solid structure here at the middle, and we have this porous structure at the end to the heat insulation. But it should be noted that this part also performs another function for the like structure load bearing. So we also have the pressure here. So in the real design, we should make the compromise between the two functions and find the optimal design which can do both have the better structural performance and also have the better like heat insulation performance. So this is the design optimization of the heat treating lattice structure for multifunctional performance. Another thing is not, my research is not only focused on lattice structure. We are also working on the composite or like a continuous fiber reinforced composite. This is a collaboration project I did when I was the postdoc research at SUTP with Professor Narashima. Now he is a professor in Washington State University. We are working on trying to design and optimize the fiber orientation inside the part and optimize the micro shape. You see the shape of part change. Also the fiber orientation also change. And we use algorithm to link those short fibers into the continuous fiber. And finally, additive manufacturing use the 3D printing techniques to fabricate this type of like a composite structure, which have the fiber oriented to the principal stress directions. So those are about optimization. And another like a major research area I did is for the digital modeling of the hybrid materials. As I mentioned before, visualization and modeling is another challenge for the hybrid materials. So existing CAD software, this is existing most commercial CAD software, no matter which brand, CATIA, NX, cannot support design the digital hybrid materials. Existing CAD software cannot support modeling the part made of functional grade digital materials. And also it is hard to simulate the functional performance of digital hybrid materials. In order to solve this problem, this is a research I did when I was at the Singapore University of Technology Design. We are working on the next generation of the CAD software for the additive manufacturing to support the design and the fabrication of the digital hybrid materials. So we developed a concept called the material template. So the idea of this material template, we want to use this type of the template as a standard way for us to describe different type of the digital hybrid materials. Range from for example, for the lattice structures, the fiber reinforced composite, short fiber, continuous fibers, and also we want to describe the voxelated materials. And this template we have for node descriptor list, constituent materials, position information, and primitive information. And we define the descriptors on the descriptor list. This descriptor is trying to use to characterize like a microstructure or mesoscale structure of the materials. Here, I give you one example about the template of the like lattice material, lattice structures. And we define the like a lattice unit cell inside the primitive topology in the primitive information like a node. And we use this tree structure to describe how to construct a single unit cell. And in this template, we have we have only one descriptor, which is about struct diameters. This diameter of this strut is trying to describe the relative density or the porosity of the lattice structures. Oh, I think I have another like descriptors, which is trying to control the cell size. This is about the lattice, which is quite easy to model because it's periodic. And we also trying to model some like stochastic digital materials. This is a stochastic digital materials we developed. It's a short like fiber. We can use the additive manufacturing process to precisely control the fiber lengths, diameters, orientations. And in this template, because template is really long, I didn't attach all the like detailed information here. If you're interested, you can read my papers. But here in this template, we totally have the 9 descriptors. These descriptors is trying to control the randomness of those fibers. For example, this sigma theta is about the standard deviation of the theta angle. Is the angle of the like fiber. We use a different value. You see, we can use a different descriptive value to have the different randomness. And Vf is the volume fraction. We can have the different fiber volume fraction. And we can use the method we developed. We can have the functional gradient, like a randomized lattice structures. This one is shows the distribution of the theta. And so we have the red region to the blue region. And then you see the fiber orientation gradually change into the like from the horizontal direction to the vertical direction. Actually, yeah, this is the demonstration of the how can we control the random hybrid lattice structures. And another thing is about theoretical digital hybrid composites. So we can combine the lattice with the short fiber. So for the thread of the lattice, it's not made of the conventional like metal polymers. It's made of another digital materials, short fiber reinforced composite. So we can control the like the lattice, like the diameter and the cell size, and then for each lattice thread, we define its material is the another digital material. We can use the short fibers. We can control the fibers distribution orientation inside each lattice thread. So we can have the much more design freedoms. This is a short, yeah, we use the polyjet printing process, print the like functional gradient lattice fiber hybrid theoretical digital hybrid materials. And you see that on different scales, we have the different like meso or microstructures of the materials. This is idea how we do the modeling. On the scale 1, we have lattice. On scale 2, we have the fibers. And then we develop the code in the CAD software. And actually, we developed a plugin at that time in the NX, and which can generate the slice file. This slice file can directly read by the additive manufacturing machine and then print layer by layer to get the final result we have. This is the idea we have. The last one is that in the past, we just changed the material's shape. And in the research, we found that also we can change the process parameters. So we can not only like update the shape of the meso or microstructures, we can also try to use a different process parameters, try to fabricate different lattice threads. We can further enlarge our design space. This is an example about the lattice structures and fabricated by the FDM, one type of the additive manufacturing process. And we use a different here. We use a different printing like speed for the thread along the different directions, and then we can have the bigger design space, and we can further control the anisotropic material properties of these lattice structures. We can achieve different type of the lattice models on different directions, and so it can further enlarge our design space and help us get more like optimal design. If you still remember the first slide, I have talked about the computational design. Why the computational design can give us the better design result? Because it can try the lot of like design options in the big design space. So if we can enlarge design space, it can potentially help us to get the better result. This is the reason why we need to consider the manufacturing process, the process planning in the design stage. The next section, I will give you some quick introduction about implementation and some case studies. First one is about Lattice. Actually, we started developing of the software called Lattice when I started my PhD. Research at that time, we cannot find any really good commercial software, especially the open software to support us to design lattice structures. So we have some like undergraduate students to help me. We are working together to develop this type of the like pure open source lattice design software from 2014. And actually, it's a plugin in the Grasshopper. It's a set of tools for lattice structure design and optimization. And if you are interested in this software, you can download it freely from the website I attached. And this software help us to, support us to the computational design of the lattice structures. We can combine the different blocks we create in the interlattice, and this is the design algorithm to generate different type of the homogeneous lattice, heterogeneous lattice, and conformal lattice. And also we can use the software. We have the FEA interface, can output this type of lattice directly to the FEA server for the simulation. And we have the like the optimization module help you to do some optimization work. Yeah, this is show you how the optimization module like works. This is the best optimization algorithm. I published my paper in 2014, and I implement in this like a component. We have optimizers and link to the FEA server, which can help us to further optimize the for example, like this, optimize the porosity or relative density distribution of the lattice structures. And also we support the design for simulation of the lattice solid hybrid. So it means that in your design, you don't need to have everywhere is a lattice. So you can combine the lattice and the solid structures together to further improve the performance. And another software I want to mention today, now you cannot download this software because it's still like an ongoing project. And I talked to my previous colleagues in Singapore, in SUTD, and in United States. We think now we have some software which can support us to do the design of the lattice structures. But lattice is only the one type, a small type of the hybrid or digital hybrid materials. We need a design tool that can support our design and modeling of the multi-scale hybrid material, digital hybrid materials, like those short fiber one, because now there's no tool in the CAD software can do that. So we are trying to develop, now it's under developing. So trying to develop tools like the interlattice, trying to can design, support design and optimization of lattice, fiber reinforced composite, voxelated digital composite. It's still on the developing stage. And I hope the first version, yeah, because some of my students cannot come and it delayed our like developing plan, but I hope the first version can be released in the end or the middle of this year. And also we are welcome to researchers from different fields to join us, because for the lattice software is the same. It's not only used by the people in the mechanical engineering, but also used by people from architecture, from the bio, they use the interlattice to design the scaffold for the bio tissues, culture, and welcome researchers from different fields. We can have the discussion and maybe we can develop some unique component to support the design for specific like field. Next slide, I can show you some like design cases we have done based on our software. One is a biomedical implant. We have done a lot of like design cases with different collaborators. Some is a hospital, some is the commercial companies. And we use a porous lattice structures to enhance, for example, this dental implant. We use this type of randomized like lattice structure to enhance the cell bone integrations, have the like rigid connection. It's not as for the structural performance, but we want to enhance the rigid connection between your like implanted dental root with your jawbone. And another thing, actually, this is case study I did with my FYP student, final year project student last year. We designed a porous lattice shoe sole. And the idea of this lattice shoe sole is that first idea is that if you watch the video or see something about Adidas, they have the lattice shoe sole and which used for the energy absorption. And the idea for this one is one thing is that, okay, we want to use the lattice fuselage for the energy absorption, but we also want to control the properties along the fuselage. So we want to have, because if we look on our like fuselage, we will see on different regions, if we have the different mechanical properties, it can further help us to like lower down the peak PPP is the peak plantar pressure on the bottom of our feet. So we developed the algorithm based on the theoretic model to help us to optimize the porosity of this type of lattice structures to help us to further reduce the PPP, peak plantar pressures. This is a conventional fuselage with the lattice structures, with the porous lattice structures. Actually, the PPP is 313 kilopascal, and after we do the optimization, we can reach to the 66.5 kilopascal. It can reach up like it can how to say, it can decrease a lot. And another thing is that different people have a different like shape of the feet. So it means that this optimization should is the case dependent. We cannot have the universal, optimal result. The fuselage fits for every patient. So for each patient, we can run these algorithms and we can have their own customized fuselage, not only with the surface shape, but also with the material distribution on the meso or micro scale. Yeah, this is another some case studies about design of the lightweight structures for the UAV, unmanned aero vehicle, and also for some like this one is for the automobile industries, some components from cars. The last case study I want to talk about today is the design cases I have done in SUTD with my collaborator, Professor Zheng. Now he is working in the Stochastic. And what we do is that we use the voxelated material to achieve some 4D printing mechanism. And this is a digital design flow we have. If we have a like preferred shape and we do the 2D meshing and we flatten it, we calculate the curvature for each strat, and we map this result into the material distributions. Actually, the reason why it can like change the shape is because we found that during the printing process, the radial stress will store in one of the material called Tang. And after printing, actually we used another material called Vero to lock the radial stress. And after printing, if we put in the hot water, and the water temperature is larger than glassy transition temperature of the rigid Vero, and the Vero will become soft, and the radial stress will release. And according to the different amount of digital material we used, and we can achieve the different shape deform. And also we found the radial stress is not only caused by the materials, and also actual radial stress will be different based on different printing process parameters. Yeah, layer printing time will also affect the radial stress. So we do the optimization for both material and process parameters and to control the shape. So yeah, at the TMD, we developed this type of the digital tool, which can support first, we do the scanning of the human ankle brace, human ankles. We have the 3D model scan, and we have the software which can do the flattening. Yeah, this is the flattening process. And we generate the lattice, and we map the like curvature into our like material distribution for each strat. You see for each strat, yeah, because the deformation curvature is different. So we have the different soft elastomer and hard elastomer. Soft elastomer is a Tang, which have the radial stress. Hard elastomer is the Vero. And we have the different material distributions, and we also control the like process parameter as mentioned. And we do the simulation. Yeah, if the simulation are okay, and we do the voxel printing. Last we passed our design to the Polytechnic machine. This is the video. Here. Yeah, so after printing, we print the flat structure and we put it in the hot water, it will deform into a shape we want. But there are some limitations. Now this structure is so soft. So even though it can deform the shape, but the polymer is, it's like above its gaseous transition temperature is like rubber, like it's so soft. So it's still not functionalized. We are working on that, trying to like think about how to make it much stronger to support some like the real function. This is only the concept in the lab. Okay. So at the end of my today's talk, I want to give a quick summarization about the digital future of additive manufacturing, especially on the hybrid materials, digital hybrid materials. Personally speaking, I think digitalization will be the trend for the materials and the structure design for AM. And the concept of digital twin and digital thread can be used to help us to predict the performance of the fabricated part. Yeah, during our like experiment, we found sometimes the simulation result and actually experiment result varied a lot. So yeah, there are a lot of reasons. For example, during the printing, the different process parameter you use is not as what you design. And also the materials, the raw materials will change from batch to batch. And it also costs a difference. The concept of the digital twin and digital thread have helped us to update the material properties and process parameters like with the machine, with the fabrication state, can help us to have the better like prediction on the performance. Second one is that digital hybrid material open a door to design material with tailored properties, but still also bring us a lot of challenges. We cannot use conventional material selection strategies like the HB chart to help us to select the materials for the digital hybrid materials because we have a lot of parameters we can like play with on the different design skills. So yeah, we may need more like advanced optimization or computation-driven approach to help us to take full advantage of the digital hybrid materials. Additive manufacturing processes that can fabricate digital hybrid material are still limited. Yeah, if you see my case study, most voxelated material are fabricated by the Polytechnic machine, and it can only support fabrication combine the two different type of polymers. But we did some like interesting research before that if we can combine the polymer with metal, polymer ceramics, and different type of the like engineering materials, and we can further like because now 4D printing, as mentioned, is really soft after you print, so it's useless. But if you have more advanced additive manufacturing process or hybrid manufacturing process can be developed, we can fabricate more like interesting digital hybrid material with a higher like performance. This is also another field I want to investigate in the future. And integration of the process, material, and structure design will be, I think, another trend of the futures. Currently, our focus mostly likely on the material and the structure design. But process design is another like interesting field to explore. At the end, I feel that there will be some like future applications because now for digital hybrid materials, most paper are still, most research are still on the paper, not a lot of like real applications. But I think in the future we can certainly have some like real applications. For example, software robotics. We think about use the hybrid material to control as a like smart material as actuators for the software robotics, control its behaviors in the different temperatures in the different environment, smart wearable devices. Recently, I have a collaboration with the professor from the IIT. We are working on trying to put some, like they developed a special ink which can code on the lattice eye design. So we can use a lattice structure for, yes, for the shoe sole and to absorb energies. And also, if we put some like special ink on that lattice, it can also be used as a sensors. So we integrate the structure integrate the sensor in the structure to monitoring, yeah, how you walk, how you run, and those data. And some smart structures and advanced manufacturing. I think for the lattice structure in the past, I did a case study with one of our industrial collaborators. We use the lattice structure for the heat dissipation, for the convection cooling. For the injection mode, it performs quite good. I think we can have some further application in these areas. At the end, I want to thank my collaborators from different universities, companies, and hospitals And thanks a lot for actually a lot of like research projects is like in the collaboration with them. They give me very good like interesting input, and we did really good job. Thanks a lot, and thanks for your attention. If you have any question, please let me know.
Okay, thank you, Dr. Tang, for your very impressive presentation. And firstly, I think I would like to welcome Dr. Mirkhalaf from the
thank you.
University of Sydney. Hi there.
Hello everybody. Hello everybody. How are you, Yunlong, and also Zheng? I'm so sorry. I'm so sorry everybody. We faced a problem this morning with the internet, so I was on the phone for an hour with the troubleshooting guys, and so anyway, it was it was a headache.
No worries. You catch up with the time. You didn't miss anything, so no worries. So I think perhaps we can move to the Q&A session, and perhaps I think Dr. Mirkhalaf can lead this session. And is there any general questions from the audiences, by the way?
Yeah, would be a pleasure, of course. Yeah, any questions? Yeah, I would love to have a chat about this as well. It's great. It's fantastic. The extent I was there, it was quite interesting. Yeah. If there is no questions, I can actually.
Yeah, I saw one people.
Oh, there is raise a hand. Yeah, please go ahead. Who's that? Everybody.
Hey,
Yeah.
hey, Dr. Tang. Yeah, it's an awesome talk. Thank you for that. Yeah, I just have two questions actually. So first is about the computational design. I think it's a great design idea, and it could potentially change the future. But I do see the problem might be lies in how you specify the parameters to the computer. Let's say, for example, I'm trying to design a chair, let's say, but how would you tell the computer that you're actually designing a chair? How would it be able to understand the shape of the chair and the function of the chair? How do you actually translate it from natural language to a language that the computer could understand?
Yes. Okay. Yes. I think that's a great question. And first of all, currently we are not reached at that level. But yeah, there are two solutions. For the current solution, what we do is that we still cannot depends on computer for everything. So for example, we have the chair, we define its function, and then now what we need to do is that we developed algorithms. Yeah, we use our brain, the human like intelligence, not the artificial intelligence. We use a human intelligence to understand the design specifications about the chair and something. And then we convert to the algorithm. We convert to the design flows. We think, okay, the chair, we should have we should have some legs to support. But the number of legs can be the parameters. So instead of, yes, every chair has 4 legs, you can design the chair with 2 legs, 3 legs, 5 legs, 6 legs to see which one is better. And you can use the algorithms to driven the design. And then that algorithm will generate the design with a 6, 5, 4, and you have some criteria. Yeah, you should use your own brain to develop some criteria, for example, stability. So if the 2 legs like chair is stable enough, or no, maybe yes, if you have the little like a disturbance and it will like falling down, and so maybe 3 is good, maybe 4, and also there are another some, yeah, especially for some like product design. As an engineer, we think everything can be quantitatively measured, but another thing is about like the beauty. So sometimes, yeah, 3 legs is enough, but why we still need 4 legs, or sometimes 4 legs is good, why we don't like 5 legs? It's about yeah, different people think about, okay, this is beautiful like chair. Another one looks ugly. So you will also, yeah, human will also play a role inside, yeah, the selection stage.
Okay.
And
Yeah,
all the
yeah.
things will be integrated into the design algorithms and the flow, which I show on my slide. There is a design flow. You can use that one to define how you combine those legs. But this is the kind of stage. And I think in the future, computer can do more. Yeah, this is some talk I discussed when I was in the SUTD with a professor from MIT who did the artificial AI-driven design or AI-aided design. Yeah, we think the kind of CAD software is still, frankly speaking, I call it silly because everything we need to use our hand to do that. And I don't know whether now you have the experience to use the PowerPoint, make the slide. And if you insert an image inside your, like in your slide, then it will give you some options.
Yeah,
and
generate some design ideas.
Yes, different. And I don't know what algorithm they used in the at the back end, but I think in the future it can be the data driven to collect. We have the big data, and for one function, we have a lot of like concepts, a lot of like a design algorithm stored, and then we will do the matching. Yeah, we will see how similar is like the Google search, but it's not like a search text, but search the like technical specifications and search how similar between your design requirement to existing design algorithms. And then we can directly mapping, and then you have the template. You just need to do a slight modification, and you can reuse that code for your design. Yeah, I think that will be the future of the AI-driven design.
Oh, okay, yeah, that's actually a great idea. And I'm also thinking it might also be useful. Let's say if you have an algorithm that already clustered the things into different clusters, and you tell them, for example, I need a chair, and it grabs a kind of like a chair from a cluster, the chair cluster, and optimize based on that. I think that would be very interesting. Okay, cool.
One of my colleagues in SUTD actually, he did some really interesting research, but not for the design, but for he called the design ideation. So if you want to do something, you don't have any like background information. Yeah, they based on the knowledge map can help you to figure which area you should look for the solutions. I think this is another really interesting like stuff to explore.
Okay, cool. Thank you. Yeah, I also have another very quick question. So, the intra-lattice software that you developed, I think it's very helpful because I was once trying to design some lattice structure, but I couldn't find a open source software. So I'm just wondering how are you actually how is the workflow in that software? What do you use as input, and how do you get the lattice structure?
So yeah, so for the workflow, let me see. May I share my screen? I think I have the. Can I show my screen? Yeah, can you see my screen?
Yeah.
Now this slide. So actually, this is for the lattice. So for the lattice, as I mentioned, yeah, for different type of, as mentioned, why we do the classification of the lattice, because different lattice structure, different type of lattice structure have the different workflow. Yeah, this is I call the periodic lattice structure. So the workflow is that you choose this component is called select the lattice topology, and then this component you can input the lattice the cell size and generate the frame, and the frame can be like we call the thickened frame. Yeah, after its generation, the frame will be the like a very thin, like it's holding a lot. And after you thicken the frame, you can have the thickened frame, and you can have the homogeneous, you can have the heterogeneous. So you can control the radius or thickness for each strat by strat. You can have a finally like homogeneous lattice structure. So this is a one like flow. But for other type of the like lattice structure, we have a different design flow. For more like detailed information, yeah, if you're interested, you can email me and I will send you a document. Yeah, we have a document how to use the different flow. Also, another very interesting thing is that I found because it's open source, so a lot of our users, they based on our like some of our components, they developed their own like workflow. Because before I go to the SUTD, Singapore, and they have their customized version of the intranet. Yeah, most component is from original intranet, but they have their own flow to enable to design some like a twisted lattice structures. The strats no longer the straight, it's a twisted. That's really interesting.
Okay, that's awesome. Thank you very much.
Welcome.
Yeah, it's fantastic. This gradient structures is not easy to make if you want to start from scratch, especially when you want to connect the unit cells together. I think it can be a for researchers. So yeah, that can be quite helpful.
Yeah. Yeah, the reason we developed this is at the beginning of my research, I found it's really difficult. So we decided, okay, we need to develop something and make it open source, available for everyone to use.
I think there is another question from the general audiences. So what is the state of the art of digital material design used for designing energy conversion, especially for the energy harvesting or storage devices?
Yes, sorry, I'm not expert in the energy harvesting or devices, but I see there are some like interesting research. They use this type of the like porous materials for the damping, but yes, trying to convert the mechanical like energies, yes, the motion energies into like electrical or but in my part, I working just for sensor. Yes, we just trying to to collect the signals for the vibration. But I see that there are some research, trying to use the porous lattice structures to absorb the energies and convert to the electricities.
But have you considered about the thermal properties in your design process?
Thermal.
Thermal, yeah.
Okay. Yeah. So yeah. What type of thermal properties?
I don't know.
Yeah, it's actually my question. Yeah, actually, thank you, Dr. Tang, for your very interesting and very informative presentation. I'm not really an expert in material science or solid mechanics, but I just wonder, like in this kind of simulations, have you considered things like heat conductivity, or can this material design modeling can actually consider heat transfer, so that you can use this to design, for example, engine or some applications that the thermal effect is important.
Yeah.
I don't know. Yeah.
Yes. Actually, yes. Thanks for this question. And in the past, I've done a project. Because if we look at the lattice structures, and it is quite like a surface to volume ratio is quite high. So also it's when you want to pass the coolant through the void of the lattice structures, it can have some like a turbulent flow, which can enhance the like a heat convection. So if we pass the coolant through it, and in the past we did a project to use this type of lattice structures put inside the injection mode, and for the purpose of the like a conformal cooling. In the past, for the cooling channel, it will be like a cylindrical cross-section shape. And we found if we use the lattice structures, it can have a better like a heat convection performance. So we can cool down the mold really quick. So it can shorten the production time. So in the past, one part will like take 6 minutes to like a whole cycle of injection mode, but with the lattice structures, it can reach to 4 or 3 minutes. But practically speaking, if we go to industry use, there are some issues. One issue is that for the lattice structures, and if you pass the coolant, and especially there are some small particles inside the coolant, the small particle will hit the lattice structure. It's not like a circular, like a very smooth, because the lattice structure, even though you fabricate it by additive manufacturing, will hit the structure, and it may break the structure. And because for this type of like a cooling, and those like lattice structure also under a certain load, and maybe will make the mold cracks. And we found that the fatigue life, the life of mold, has been lowered down compared to conventional cooling injection molding. Yeah, another thing is that we also found that the lattice structure will make some, we call the dead zone, because if you do the fluid analysis, dynamic fluid analysis, you will see that in certain small region, the fluid velocity is really, really low. And heat will accumulate in those regions. And this is also not preferred. So there are some like advantages and also disadvantages. But the potential research is that we can do is trying to, instead of use this type of regular lattice, we can design some special type of the lattice structure, or maybe use the I think people use this type of wait a minute. Yes, this George lattice structure, surface-based lattice structure. Yeah, for the cooling, maybe can have the better performance, because this one is much more smooth and can try to avoid the problem I have mentioned.
Right. So, like, what's the length scale of this small pores you're talking about?
Yeah, so you can control the size, depends on your applications. You can control the size. It can be nano, or if you can fabricate it. Yes. Now another thing is that, as mentioned, the manufacturing process is still the constraint. Yeah, from the design part, we can design, even though we can design in the like atom scale, but for the fabrication wise, we cannot fabricate on that scale.
Okay. Because if you say like in some applications, the purpose is to suppress this turbulent motion of the coolant. Maybe you can reduce the size of these pores so that the length scale is very small, the Reynolds number is very low. Then like the flow across it will remain in the laminar regime. Yeah. I know like for computing devices for the cooling. If they actually avoid to have like two small scale fins, because that suppress the turbulent cooling, right? They want to have some turbulent cooling to enhance the heat transfer rate.
Yeah.
In this case, maybe it's the design purpose is the opposite.
Yeah, that's a good suggestion.
Yeah.
Thanks.
Yeah, thank you for your answer. Yeah, very informative. Thank you.
Thanks.
Zheng, do you want to ask your questions? If nobody else has questions?
Yeah, sure. Like if nobody else has, Does anyone else has questions? Okay. Oh, if no, I can have my questions, because I'm quite interested in the multi-scale topological optimization. So I know this optimization method, but I didn't really dig into that before. So what's the resolution of this method optimization? Because I saw that you have to tesselize certain space, and then based on that as a starting point to optimize it. So I'm just wondering about the resolution and about the computational efficiency regarding the resolution of the optimization. Yeah.
Yeah, you mean this one?
Yeah, I think so. Yeah, this one. Yeah.
Yeah, so that's a good question. So to optimize the lattice, there are several different ways, and the question for the resolution is really good, because one way is that very simple way is that we can take each lattice strut as a design parameters.
Yeah.
Each lattice strut as a design parameters. But if you have a very large structures, you have the billions of the lattice strut. You will have the billions of the design variables.
Yeah.
And it will make your the optimization algorithm converge really slow and
Yeah.
takes a long time. So
Yeah.
what we do is that we are trying to use the topology optimization.
Yeah.
So for the topology optimization, we have we define the design variable inside each element. We consider we divide the design space into several solid elements. So the size of element is bigger than the cell size of the lattice structures. And then we do the optimization. We get the optimal relative density distribution. For example, for this one, if we have the millions of the lattice cells, but we only have the thousands of the elements. So we have thousands of elements. We use the mapping function to map the element to the cell properties.
Yeah.
And then we get the heterogeneous lattice structure. This is the idea that we want to make it computationally efficient.
Okay. So a follow-up question would be that because the topology is that it's kind of like a very kind of like a simple way to expand the topology is that like how many holes in the geometry. So I'm just wondering like because you're always starting with topology with no holes, and so it's kind of starting point. But well, is it all right if you're starting with the topology with one hole or two holes? Will it affect your results? Or
Yes, for the topology optimization, theoretically speaking, there are different optimization approach.
Yeah.
And there are some approach we call the level set approach.
Yeah.
So for the level set approach, you can start with several holes, and those holes will be during optimization, the algorithm will driven the hole will be merged together or disappear or whatever.
Okay.
So no matter theoretically speaking, it's all actually it depends on a lot of factors. But theoretically speaking, the optimal solution will be the same, no matter which start point you are from.
Okay. Yeah, I see. Yeah, that's basically is my questions. 2 questions. Yeah. Thank you.
So anybody else, please raise your hand or unmute yourself, speak up.
So perhaps I have one more question, because in your future work, you mentioned about the twin, right? Digital twin.
Yeah.
So I know that perhaps in your the shoes making, the prototyping, you are embedding some sensors onto that so that you can detect or in real time, like the distribution of the pressure or others for the simulation or dynamic simulation purposes. But actually the question would be that because I think the generative design you proposed or computational design is rather a kind of based on the design constraints, which is a rule-based kind of way. But if the simulation model under such a one is sort of like the physics-based one, but now you have the data-driven method, which can be an AI-driven one. So how you can combine or how you can make that happen for optimizing your design in a rather data-driven manner or in real time, how you can make that happen?
Yeah, I think that's a really good questions. And in the past, it's like the design is one round. So you design the part, you deliver to the customer, and then it's finished. But I think you are expert in this area. So if we put a sensor on our shoe sole, and we can get the more detailed distribution, because in the design we have a lot of assumptions. So we'll assume the weight of the, for example, you may ask me, how can you get these figures? And can you prove that your simulation model is really accurate? And now my answer is no, because I have a lot of assumptions. And I assume that, yeah, your food, the property, mechanical property of your food is like in this level. And then, yeah, the printing is perfect and you're working like a gesture, the giant, we call the giant, is in the desired mode. But for every customers, every people have a different, for example, different elastic models of your food and different like working like a style, and you may have a different like distribution of the stress. And so the question, yeah, your question is quite good. Now, I think some future research is needed to consider how to incorporate those data into our CAM design flow to correct. It's like the control system, and we should have like a feedback closed loop control. Now it's open loop control. Yeah, from design to the manufacturing to the delivered product to the customer. So we should have the closed loop control and use the data we collect to calibrate or to the offset the simulation we have in the design, and then use this data to like to predict use the data-driven method. Yeah, the data we collect from the patient or the users to correct the simulation model. And based on the corrected simulation model, we can do the optimal design. For example, if for this one, after, yes, we put, yeah, we ask the patient to wear the shoe sole. And we found, okay, the pressure here is still high. And then, yeah, we are trying to modify our design. Maybe, yeah, make the material here softer, trying to see how it will happen. Yeah, this is just an idea, not really like have the thorough thinking, but hopefully it can work, but needs some future research.
Thank you.
Any other questions? If nobody has questions, I'm also curious about a couple of things. It's just it was very interesting when you talk about the 4D printing thing, and I was thinking that are there any oh, time is up, so I try to ask very quickly. Is there any way to add some to that polymer that are also activated at high temperatures, so but operate at a longer time? So the temperature derived shape changes first, and there are some cross-linkers inside the polymer that can cross-link the polymer further to make them harder at that temperature.
Yeah, I think that's possible. Yeah, that's totally possible. So we should, yeah, that's the one possible way that we can make those like a 4D printed like structure much more stronger than, yeah, in current like design.
Yeah, yeah. Also, I was curious when you design this gradient structures. So the relative density of each unit cell is derived from the stress. Like higher the stress, the higher the density in the final product. The higher relative density in that lattice unit cell, basically. But how are these unit cells are connected to each other? Because one gonna be a little bit less porous or more porous than the neighbor, yeah? I assume the unit lengths are the same, but the strut thickness is different. Are these attached to each other, or there's a transition kind of in between? You know what I mean?
Yes, you mean that currently, actually, what we do in most heat treatment lattice, there are two ways. One is that, yeah, if you have the same stress thickness, and you can change the cell size. If you have the same stress thickness, and you can change the cell size. But if you change the cell size, there will be the transition. But what we do is that we didn't change the cell size. We changed the stress thickness. So stress thickness will change on a different region with a different stress thickness, and the relative density will change.
Yeah, yeah, fascinating, really.
Thank you.
Thank you. So if there is not, yeah, Zheng is telling me that time is up. Don't ask too many questions. I'm just, yeah, it's just that I love have this chat about science and these things. So no, I'm just joking. Jen is just gently saying that time is almost up. So probably, yeah, if there is no question about this very really fascinating talk, we conclude the session. If there's any final words from the panelists or from our speaker, please go ahead. Otherwise, we just say goodbye, I guess.
Yeah, goodbye and a happy new
Goodbye.
year.
Oh, happy new year to everyone.
Yeah.
Bye-bye.
Bye-bye.
Sorry again. Yeah.
Cheers.
Yeah,
Bye.
no problem. Yeah. Bye-bye.